So this presentation is called Developing a Generic Approach to Durability. And first of all, I'd like to acknowledge my co-authors, Shi, who recently graduated from Southeast University in China and spent 2 years at EPFL, William Wilson, who is now a professor at University of Sherbrooke in Canada, and Fabien Georget, who is still a postdoc in my group. Now, what's the rationale for this study? Well, if we're realistic about things, the composition of cementitious in the future will continue to be based on Portland cements with increasing incorporation of supplementary cementitious materials, as this is by far the most effective way to reduce CO2 emissions. Now, unfortunately, the classic SEMs we've been using for many decades, like slag and fly ash, are in increasingly short supply. Today, there's about 15% compared to the demand for cement, and this is decreasing due to the fact that we want to stop burning coal, that we want to find less CO2 intensive ways of producing iron. So we need to be able to use new sources of SEMs, notably calcined clays, which are extremely interesting in this regard. And to minimize environmental impact, we need to be able to optimize our cementitious materials according to which materials we have available locally and the application. And then we need to be able to predict what will be their service life to users to have confidence in using these materials. And there's no way we can empirically test all the many thousands of combinations possible. So we have to be able to develop generic approaches. Now, fundamentally, a generic approach should be based on understanding the microstructure. And in terms of the microstructure, we have, first of all, the chemistry, which is which phases are present. And this now we know fairly well because we can predict this based on thermodynamic modeling. We also, of course, have the pore structure, which is very important to look at. And when we first started this work, we thought that these two things together would be sufficient for us to predict durability in this generic way. Unfortunately, what we found and what I'm going to show you today is that it's rather more complicated. There are a number of other factors. One particular factor that's important is the pore solution, but we also have perhaps things like surface interactions we need to understand better. So we first looked at this with this system of 7 binders. We took a reference Portland cement, and then we had ternary binders in which 30% of that Portland cement was replaced either by calcined clay, by slag, or by fly ash. And then we had ternary binders in which a further 15% of the clinker was replaced by limestone. Now, if we look in terms, and this has already been published last year, so you can look at the results in more detail. If we look at the strength of these systems, what we see is that at the beginning, there's quite big differences in reactivity. The calcined clays are more reactive, so they have higher strengths at early ages. But by the time we get to 90 days, these systems all have a very similar strength. And we decided to focus on chloride ingress because this is well known to be the most important cause of concrete degradation. A good example here is this motorway interchange in Montreal, where you can see quite heavy amounts of corrosion due to the penetration of de-icing salts. And now if we look at the chloride penetration for these same 7 systems, you see, even though they've got the same strength, the same water-cement ratio, the chloride penetration is dramatically different. The black line here is the reference Portland cement with very deep penetration even after 6 months, whereas the slag considerably improves things with about half the penetration depth. Things are improved yet again with the fly ash, and the best systems are those with the calcined clay, and particularly the calcined clay with limestone. So we wanted to see how these quite dramatic differences in diffusion, apparent diffusion coefficient could be related to the microstructural parameter. We looked at the physical effect first of all. We could characterize the porosity by mercury intrusion porosity. You see, in general, the supplementary cementitious materials have a considerable refinement of the pore structure. However, when we look in detail at the parameters from the pore structure and their relation to the apparent diffusion coefficient, we really can't see any systematic relationship. The total porosity is very similar in all systems. This is not surprising because they had very similar water-cement ratios. The critical pore size is varying quite a lot, but not in any systematic way compared to the diffusion coefficient. And unfortunately, it was a similar story where we looked at the calcine, at the chloride binding. These are the binding isotherms. We see some variation, but again, when we plot these against the chloride penetration, there's really no systematic relationship. So what's missing? Well, we thought, of course, of the pore solution. And when we looked in the pore solution of these systems, we do seem to see quite a nice trend between the apparent diffusion coefficient and the concentration of alkali, sodium and potassium in the pore solution. And intuitively, this can be understood by the fact that chloride is a negative ion. So to charge balance, you need positive ions. And the more sodium and potassium ions you have in the solution, kind of the easier it is for the chloride ions to be in solution and therefore to move through the system. But as we'll see, this is still not sufficient to explain everything. So we then went on to another example where we looked at two systems. Well, we looked actually at a lot, but I'm just going to explain you just two systems. And particularly, we took into account now a variation in the water-cement ratio. So we had OPC systems here. We had LC3 systems, which are 50% of the cement, 30% of the calcine clay, 15% of limestone with a bit of gypsum addition to give us a proper sulfation. And we made these at 3 different water cement ratios. And we did various measures of the transport. The simplest one is using resistivity as a rapid indicator. And already here you can see the very dramatic difference. You can see that the LC3 systems have much, much higher resistance than the OPC systems. And yes, there's a trend with water cement ratio, but the system of OPC at the lowest water cement ratio here still has a resistivity much, much lower than the calcine clay system, even with a much higher water cement ratio. And the other measurement of transport we made was to use these mini migration tests. This paper has also been submitted for publication, so hopefully you'll be able to read it soon. And here we looked at the current pass, but we also looked at the chloride accumulating in the downstream cell. And we could see from this get effective chloride diffusion. And again, we see this very dramatic difference between the two systems. Again, of course, we see water cement ratio is important. As you increase the water cement ratio, your diffusion coefficient goes up. But again, the differences between the two binders are much, much greater than what we can get with water cement ratio. So in this case, we used a number of other methods to look in more detail at the particularly the pore structure. We looked at the total porosity. We see basically the total porosity in the OPC systems is pretty much the same, if not a bit lower than the porosity in the LC3 systems. Of course, then the pore size distribution could be different. So we looked at that using this proton NMR technique where we can divide the different pore populations into CSH gel, into hydrate pores, capillaries. And again, we don't see the differences we would expect. Systematically, we generally see that the LC3 systems, if anything, have slightly higher porosity than the OPC systems. So again, simple measures of the porosity do not explain these dramatic differences in chloride penetration. Where we do seem to see something is this so-called formation factor. But I'd like to say at the outset that this concept of the formation factor is kind of a circular argument. You're saying, what's the resistivity of your bulk material compared to the resistivity of the pore solution? And this is obviously saying the same thing as how difficult is it for ions to transport through the bulk material. Now, conceptually, people have equated this idea of tortuosity by the fact that ions have to take a longer path in the real material compared to a straight through path. And if we make our measurements here and we get values for the tortuosity, we see that these values for the tortuosity are extremely high. And it's very important to realize that values in this range of several hundreds cannot in any way be explained by simple geometry. So I made a simple schematic to explain that. This is the geometric idea of tortuosity or formation factor, that here you have a pore going straight. So the path along here is the minimum. And then in the real system, the pores don't go straight. They are quite bendy. So the ion has to move much longer. But the kind of geometrical tortuosity in these cases here is maybe 3 here, maybe up to 10 here. It's nowhere near the values of 100 we're measuring. If you wanted to have a value of 100, perhaps you could make this very, very complicated path like this. But in reality, you don't have one single pore that's not connected to any others. In reality, you have lots of superimposed pores, and now you can quite easily see that the path an ion can take is much, much shorter. It's much, much more similar to these values here. So it's really important to understand that these measurements of tortuosity go far beyond what we can imagine from simple geometry. Really, these measurements are hiding something else we don't yet well understand. We saw also in these systems that we get quite big changes in the alkalinity, which also seem to show some relationship to the conductivity. But again, this is explaining perhaps half the variation. Now, I've got quite limited time, so I can't explain all the work we did, because overall we looked at many, many systems. These are all shown in this graph here. So we've got water cement ratio as a variable, we've got Portland cement, we've got white cement, we've got slag cement, we've got fly ashes, we've got things with grass powder. And what we do see is now this very, very clear relationship between the effective diffusion coefficient and the bulk conductivity. So this is very nice, because the bulk conductivity is a very quick kind of test to make. You could measure this really in a few minutes. So the take-home message of this is that chloride diffusion is actually a complex function, that of course it has some bearing on the porosity. Of course, the pore conductivity is important. Of course, the pore solution conductivity is important. And there's probably a lot of other things here which we're trying to better understand with our further work. None of these parameters should be taken in isolation. So when you look at this relationship here, what you shouldn't do is normalize your bulk conductivity with the pore solution conductivity, because then you lose a good part of the correlation. So to summarize, I think I want to underline that in the case of chloride diffusion, all SEMs are very effective at reducing chloride ingress. This combination of calcined clay and limestone, which we call LC3, is particularly effective. And this is generally explained in terms of pore structure refinement and binding. But in fact, it's not so simple. We see that the alkalinity of the pore solution plays a big role. And then we see that there's this vague term tortuosity. But what we call tortuosity is much more than just a simple geometric change in the pathway in the pores. On the positive side, we see that these diffusion coefficients correlate very well to reactivity. But if we really want to achieve our goal of this genetic approach, we need to better understand what are these hidden mechanisms behind what we measure in this term tortuosity and formation factor. So I'd like to thank you very much for listening and hope I've left enough time for you to ask a few questions. Thank you.